Welcome to the second lecture of module 2 on mass transfer operations. In this module, we are discussing equipment for gas liquid operations. Before going to the next lecture, let us have a small recap on our previous lecture. In our previous lecture, we have considered different mass transfer equipment both for batch and the continuous mode, and those equipments are sparged vessel, then Venturi scrubber, agitated vessels, weighted wall column, and we have also said the tray and packed column. This tray and packed column are commonly used in industrial application, particularly in case of absorption and stripping as well as in distillation. So, we will put more emphasis on the tray and packed column in our next discussion. So, let us start with our tray or packed column. You can see this is a typical look of tray column. As you can see in this column, you have the different terms used over here, already written over here. BP represents the baffle plate over here, and we have column support which is over here. Then we have demister which over here, and then downcomer DC is over here where the liquid comes down. We will discuss more about it, downcomer. Then downcomer plate. So, here this is downcomer plate, and then gas inlet. We have gas inlet at the bottom, and then we have gas outlet nozzles over here, then liquid inlet which is at the top, and liquid inlet or side stream outlet. So, which is over here. Then we have manholes. You can see over here manholes are written. So, manholes, through manholes when the cleanings are required, it is used. And then we have nozzles, then we have reinforced concrete foundation, then sieve tray. So, each tray has a perforation, and you can see the tray which is sieve like, you have learned in your mechanical operation course. There are different kinds of sieves used. So, it is called sieve tray. Then tower cell TS, and then TS are tray support ring, and then weir. So, weir actually which is maintained a particular liquid height in a particular tray. A tray tower primarily consists of a vertical cylindrical cell and a set of tower internals. This tower internals includes tray or plates on which the gas liquid contact occurs. So, for each plate or tray, the gas and liquid comes in intimate contact. Arrangement for flow of liquid from one tray to the lower one through the downcomer. So, through downcomer, the liquid which is from the inlet, it goes to the downcomer and it comes down to the next plate. Inlet and outlet nozzles for the two phases. Nozzles are provided for the two phases. The figure 1 which you can see over here schematically shows a few essential part of a sieve tray columns. In gas absorption application, the liquid enters at the top tray through a nozzle here. It flows across each tray and flows into the lower tray through a downcomer, as we have discussed before. the gas flows upward and vigorously bubbles through the liquid on a tray. So, through the perforation the gas goes up and then there is intimate contact in each tray between the gas and liquid. Then forms a turbulent gas liquid dispersion in which bubble breaks and coalescence occurs continuously. So, once there is a liquid pool on a particular tray and gas bubble through, there is a gas liquid dispersion occurs, bubble breaks and coalesces and then it forms continuously, that this is a continuous process. An average depth of the dispersion is maintained on a tray. So, for each tray we need to maintain a particular depth of the liquid. Mass transfer from the gas to the liquid phase or from the liquid to the gas phase occurs depending on the direction of the driving force. So, both way it is possible for absorption, the solute from the gas mixtures transfer from the gas phase to the liquid phase, whereas for stripping or desorption solute from the liquid phase transfer to the gas phase. For example, gas absorption, the solute get transported from the gas to the liquid phase and the reverse occurs in case of stripping. The gas then leaves the froth or the dispersion and enters the next upper tray. The liquid flows across a tray and then over a weir to enter into the downcomer. The downcomer is a region near the wall separated by a downcomer plate, you can see over here downcomer plate, in which the bubble get disengaged from the liquid. In this way counter current and stage wise gas liquid contact takes place in the tower. Each tray acts as a stage in which the liquid flowing down from the upper tray and the gas flowing up from the lower tray come in contact. Okay. The tower acts as a cascade because you have multiple tray and the vapor and liquid flows from tray to tray. So, it acts as a cascade. The number of equilibrium stages or we call it ideal stages or trays required for a given separation is determined solely from the material balance and the equilibrium consideration. The stage efficiency and therefore, the number of real trays is determined by mechanical design and the conditions of operation. The construction and the operational feature of a tray tower and the tower internals are briefly discussed in this lecture. The cell is usually made of metals or an alloy. The materials of constructions anyway we will learn in another course or another subjects. So, here we will mostly just highlight the what are the materials used. Plastic cells are also used sometimes. The materials is selected on the basis of corrosiveness of the fluid, temperature and pressure conditions and the cost. So, based on these three factors the materials are selected and then which are usually among the plastics, metals or alloys. If the cell diameter is small, it may be made of several flanged section in order that the trays may be fitted into it and maintained when necessary by opening it. This is for the small diameter tray. So, we need to have several flanged sections and it is very easier to maintain whenever it is necessary. Tray towers of diameter less than 1 meter are rarely used. On the other extreme, towers as big as 10 meter in diameter are known to be in use. So, in industry you would find very bigger diameter tower is generally varies between 7 to 10 meter diameter. Cell thickness is calculated by using a standard vessel design code. So, that would be available in this references you can use, where the thickness of the cell can be calculated. A tower is generally skirt supported on concrete foundation. As we have shown you on the figure, there is a skirt foundation or support which is made of concrete or so to keep the tower. The support should be strong enough to take the column weight, the liquid load and the wind stress. Generally the columns are very tall, close to 50 meter in the height. The seismic factor at the particular location is also needed to be considered during column and support design. Since the bending moment due to wind load is maximum at the tower bottom, it is a common practice to use different wall thickness for different sections of the cell. So, depending on the bending moment or due to the wind load and several other aspects, the thickness of the sections or of the wall of the tower may be different. The bottom section has the maximum thickness, whereas the upper section has gradually smaller thickness. This strategy substantially reduces the weight and hence the cost of the cell. So, these are very much required. Instead of making the uniform thickness throughout, it is better to design as per the requirement or may be made accordingly. Trays are also called plate. So, either we can call it tray columns or plate columns. There are quite a few types of trays in use. Major function of tray is basically it allows the gas to flow through the holes or passages. So, the tray will allow the gas to pass through the holes on the tray. The gas vigorously bubbles through the liquid to form a gas liquid dispersion. When the liquid comes down from the downcomer of the upper tray, there is a liquid height maintained and the gas which passes through the perforation of the plate, it bubbles through the liquid. So, while doing so, it make a gas liquid dispersion and it create a turbulence and hence increase mass transfer coefficient and gas liquid interfacial area. So, the tray holds the dispersion on it. So, these are the major functions of a tray. The tray separates the column into a number of compartments, each of which constitutes a stage. So, that is why we call stage wise contact. So, what happens? Mass transfer between the phases occur on a tray. Therefore, the trays as a whole constitute the heart of a column. The performance of a column depends upon the performance of the trays. So, that is why tray has to be designed properly. There are different kind of trays and now we will discuss on the bubble cap tray. The bubble cap tray consists of two major components. One is cap slot, a bell shaped cap, you can see over here bell shaped cap, and then there is a riser or chimney, so which is given over here. A ring gasket is used below the nut. So, there is a gasket which is used over here. So, below the nut. The riser is a piece of tube with a flared or expanded bottom end. So, you can see here. So, the bottom is little expanded or flared. It is a tube like arrangements and then the riser acts as the vapor passage and holds the cap. So, this riser when you put cap over here, when there is a flow from the bottom, so cap will go off and the opening from the riser will also go up. So, the vapor will go out, it controls the vapor passage and it also holds the cap over it. The riser is inserted through a hole on the tray floor and the bell shaped cap is bolted to it. Now, the cap and the riser are made of low carbon steel. So, here its materials of construction usually is low carbon steel or stainless steel or any other suitable materials that can withstand the environment within the tower. So, depending on the application, the materials may be changed. Caps are arranged on a tray on equilateral triangular pitch with a row normal to the direction of the liquid flow. Bubble caps generally range from 1 inch to 6 inches in diameter. Now, we will discuss about the sieve tray. In this figure, you can see this is the simplest type of tray in which the bubble caps are replaced by holes or perforations for entrance of the gas into the liquid. So, instead of giving a cap and making a riser through which the gas used to pass, this can be replaced with the normal holes on the tray, and which will give the passage of the gas into the liquid. The holes are of relatively small diameter, usually ranging from 1/8 to half inch. This is why the name is sieve tray and also called perforated tray. For clean services, we use of a hole diameter of 3 by 16 inch is common, very common, 3 by 16 inch. For liquid that foul or catch deposition, a hole diameter of half inch may have to be used. So, if the liquid which will may clot or foul the tray holes, then in that case the larger size holes may be used. In vacuum services, 1/8 inch hole diameter is preferred. The role of a small holes: enhance tray capacity, reduce entrainment, it also reduce weeping. We will discuss all this entrainment and weeping phenomena, how it happens based on the gas liquid flows. Promote froth regime operation and also exhibit better mass transfer characteristics. So, if the holes are small, it helps in this manner. Now, we will discuss the valve tray. The valve tray is a relatively new class of tray that provides variable area for the gas and vapor flow depending upon the flow rate or throughput. You can see over here, there is a normal vapor which is coming to this, and then you have a tray, then there is a particular height of liquid it maintains. When vapor flow rate is low, opening is less. When vapor flow rate is more, opening is more. This is why it is called a valve tray. A valve tray is proprietary tray, and a common valve tray has sufficiently large punched holes on the tray floor, each fitted with a movable disc, generally circular disc. A disc has guides that can slide vertically up or down along the thickness of the tray floors. The opening for the gas liquid changes in this way, but the disc is always held in the same vertical line. As the gas flow increases, the disc automatically rises. It settles down at low vapor rate to prevent weeping. Weeping means the liquid drops which will flow very slowly through the perforation. So, that this will prevent the weeping. The guides or retaining legs are bent at the end so that the disc does not pop up or gets detached even it at a very larger vapor flow rate. The trays do not easily acquire deposits from dirty liquids, polymers or other solids because of the up and down motion of the discs and guides. So, this helps in this design, and also you can have large number of perforations, and also it take care different low and high viscous liquids. Valves units are therefore self cleaning, and the valve tray is a good choice for highly fouling services. So, if some materials will fouls on the perforations, this type of valve tray is generally preferred. In addition, they offer lower pressure drop than the bubble cap type, and generally they are cheaper than the bubble cap. There are few problems in case of sieve tray we usually encounter. So, which is also happens not only valve tray, but there are also for different sieve trays as well. Mechanical wear and corrosion because of continuous movement of the valve legs, and sticking of the disc on the tray if there is a sticky deposition on the tray. So, sometimes because of this there is a sticking of the disc, it may malfunction the valve tray. In a common valve tray layout, 12 to 16 valves per square feet of tray area are accommodated, and because of high flexibility, high turn down ratio and relatively low cost, valve trays are now widely used for gas absorption and distillation. So, this kind of trays are widely used. Now, we will discuss now downcomer and weir. The downcomer is a passage through which the liquid flows down from one tray to the next. So, you can see the over here the gas is flowing through it, and there is a, so suppose this is a tray, perforated tray, and this is the downcomer. The desired depth of the gas liquid dispersion is maintained on a tray by using a weir in the form of vertical plate. So, this is the vertical plate which is put over here. So, and this height is properly maintained, so that or the required height is maintained in a based on the liquid depth we wanted to keep. The liquid along with some dispersed gas or vapor bubbles overflows the weir and enters the downcomer or the downspout. So, what happens when the liquid enter into a tray, it flows horizontally, and then you have a vertical movement of the gas through the perforations. So, while liquid flows through the downcomer, it takes some of the bubbles as well along with it, and it goes to the next tray. Disengagement of the gas as bubbles occurs in the upper region of the downcomer. So, there is a space which are maintained, we will come later the tray spacing, and then through the downcomer when the liquid flows down with the some gas molecules along with it, gas bubbles along with it, the upper part of the downcomer there is a disengagement of the bubbles occurs. In the lower region contains clear liquid that enters the enter the lower tray. The downcomer must provide sufficient residence time for gas liquid disengagement, so that the clear liquid will come to the next stage. The residence time is usually 3 to 5 seconds. However, for a foaming liquid considerably higher residence time is there. So, if there is a foaming for the vapor disengagement, we need to have a higher time residence time. Therefore, a larger downcomer volume has to be provided. So, for this is particularly for the foaming liquids. The clear liquid velocity in the downcomer normally ranges between 0.3 to 0.5 feet per second. This value may vary depending upon the liquid properties. The weir length may vary from 60 to 80% of the tower diameter. So, as we said, the tower diameter is generally up to say 10 meter in case of the industrial towers. So, the weir length it can be as high as 6 meter. The downcomer area correspondingly varies from 5 to 15% of the tray area. Weir height of 1 to 2 inches is generally maintained. So, it provides the liquid level in a particular tray. Now, nozzles, a tower for contacting a liquid and a vapor or a gas should be provided with a few nozzles for feed entry both gas and liquid, and then entry of reflux at the top and the reboiler vapor returned to the bottom in a distillation column. So, and also for product withdrawal from the tower. So, for these places we need to have a nozzles at different locations. The primary criteria for a feed nozzles design is, you can see, to ensure that the feed is introduced with minimum splashing. So, if the splashing is more, it may not properly distributed throughout the tray. Jetting, the velocity of the liquid feed in the nozzle should not exceed 1 meter per second. The feed should be evenly distributed and mixed with internal liquid or vapor. Now, the velocity of the liquid and the characteristics of the liquid and vapor and the characteristics of the liquid, there is a formation of mist in general. Even under normal operating conditions, a little entrainment of liquid in the upflowing vapor may occur. So, we need to eliminate those vapor which is going through the as entrainment, and in order to prevent entrainment in the vapor leaving the top tray, a pad made of wire mesh or a pack suitably bent and spaced thin sheets is fitted above it. So, at the top before going out to the tower, there is a mesh which is wire mesh generally put, which actually eliminate the mist to going out. So, is known as mist eliminator. The droplets are retained after they strike the surface of the pad. Such a device is called mist eliminator or a demister. Now, we will discuss about the operational feature of a tray column. The flow phenomena on a tray with gas bubbling vigorously through the flowing liquid are pretty complex. So, it is like bubbling through the liquid. The phenomena is really, flow phenomena is really complex. The tray internals are selected and designed keeping in view the complexity of the flow and the problems that may arise out of it. So, hydraulic gradient and multi-pass trays are generally used. The difference between the clear liquid height at the point of inlet and outlet of a tray is called hydraulic gradient or the liquid gradient. It is the liquid head which is required for overcoming the resistance to liquid flow on a tray. So, the liquid has to overcome the resistance and then flow through the downcomer. So, there is a particular liquid head or hydraulic head maintained over it. You can see over here, there is a imaginary surface, and excessive liquid gradient causes severe malfunctioning of the tray. Most of the gas flows through the holes near the middle of the tray and at the outlet weir. Mostly it is through the perforation and sometimes through the weir hole also very small amount of gas flows. Only a small part flows through the holes at the liquid inlet side of the tray. Such maldistribution of the gas or the vapor severely reduces the tray efficiency. So, we need to have a very good tray efficiency. In extreme cases, liquid dumping or back trapping may occur through the end where the liquid enters the tray. Depending on the uneven distribution of the gas and vapor, it may severely affect the tray efficiency, and also sometimes the liquid dumping which may occur in the tray through the end where the liquid enters the tray. So, if this dumping occurs, the efficiency also reduces. Hydraulic gradient is also very important quantity to be checked during the tray design. It remains pretty small for a sieve tray, but for a bubble cap tray it may be significant because the bubble caps offer a larger resistance to liquid flow. So, if the resistance is much higher in case of bubble cap tray, so hydraulic gradient is also important over here. So, because that will severely affect the tower performance. Weeping and dumping. If a very small no fractions of the liquid flows from a tray to the lower one through perforation or opening of the tray deck, the phenomena is called weeping. So, that means no, the liquid usually has to flow through the downcomer. So, and liquid, the vapor flow or the gas flow should be maintained in such a way that there should not be any liquid fall from the perforation of the tray, and only the perforation will help the vapor to go up. But if there is small fractions of the liquid flows from a tray to the lower one through the perforation or the opening, the phenomena is known as weeping. Weeping causes some reductions of the tray efficiency because the liquid dripping down to the tray below through the perforation has not been in full contact with the gas and vapor. So, the intimate contact due to the agitation of the liquid and vapor which happens in a particular tray because of hydraulic gradient it maintains, and if it falls down through the opening of the pores, what will happen? There will be the contact between the gas and liquid will not be so efficient. So, that is why it will reduce the efficiency of the tray performance. On the other hand, dumping is an extreme case of leakage. So, if the leakage or the liquid which is coming from the tray perforation is huge or extremes, then no, we call it dumping, and which if the vapor flow, it happens when there is a very low vapor flow rate and the vapor pressure drops across the tray is not sufficient to hold the liquid. In practice, a little bit of weeping may occur intermittently through the sieve tray because of the instantaneous pressure imbalance. If there is a pressure imbalance inside the column instantaneously, then intermittently there is a little bit of weeping which may occur usually in different plants or different columns. Now, entrainment. When a gas bubbles through the liquid pool vigorously, droplets of liquid are formed in the vapor space by quite a few mechanisms, including shearing action of the gas jet or rupture of the liquid film as a gas bubble burst. So, depending on the size of the droplet, its velocity of projection and the drag force acting on it. So, the above phenomena happens depending on this size of the droplet, its velocity of projection and the drag force acting on it. So, on these factors, this type of actions may happen. If this happens, due to this, the gas velocity, the droplet may descend back into the liquid on the tray or may be carried into the tray above. That is why when there is a very high gas velocity entrainment occurs, the phenomena of carryover of suspended droplets into the upper tray is called the entrainment. Now, we will discuss flooding. So, under normal operating condition, an average liquid depth is maintained on a tray. The flooding is an abnormal conditions of excessive accumulation of the liquid and simultaneous excessive pressure drop across the flooded tray. So, this happens when we have a very low gas velocity. If accumulation of liquid on a tray continues, a part or eventually the entire column may be filled with the liquid. Flooding of a tray or a column may occur because of one or more reasons. So, one of them is spray entrainment flooding. So, at a very low liquid rate, as we said, when you have a very low liquid rate, the spray height increases as the vapor velocity is increased. The spray may eventually reach the downside of the tray above, causing a substantial carryover of the liquid droplets and leading to the flooding of the tray and the column. So, spray entrainment flooding may also occur. And next is the froth entrainment flooding. So, if there is no excessive froth appears on a tray over a range of gas and liquid flow rates. So, depending upon the flow rate of the phases and the tray spacing, the froth may almost fill the entire space between the successive trays. So, if there is a blockage due to the froth formation, most of the liquid droplet suspended in the gas are then carried into the upper tray, causing liquid accumulation thereon and eventual flooding of the tray. So, excessive froth entrainment can also cause the flooding of the column. If the liquid is prone to foaming or on aeration, flooding may occur even at very lower gas velocity. Another is the downcomer flooding. So, when the liquid flow rate is high, the rate of flow of the gas and liquid dispersion into the downcomer also becomes high. So, because of high gas flow rate, there will be vigorous mixing in a particular column, and there will be large number of bubbles, and which will be carried by the liquid towards the downcomer. If the downcomer cannot accommodate the dispersion load and the gas liquid disengagement does not occur properly, the aerated froth liquid fills the downcomer and finally backs off onto the tray above, leading to the downcomer flooding. Okay. One strategy of overcoming the problem of downcomer flooding is to provide a larger tray spacing. So, if we increase the tray spacing, probably that will eliminate the downcomer flooding. Now, let us see the performance diagram. Here you can see the how the column can perform under different vapor rate and the liquid rate. The performance of a particular type of tray depends upon the relative liquid and the vapor throughputs. The effects of the phase flow rate on the performance of a sieve tray are qualitatively shown in this figure over here, figure 2. This is also called a tray stability diagram. Now, let us assume that the tray operate at gas and liquid rates corresponding to point N. So, at this location in the region of normal operation. So, we call it normal operation in this figure, and if we keep on increasing the gas throughput at a constant liquid rate. So, let us keep the liquid rate constant over here, and we increase the gas flow rate or the vapor rate. More liquid is entrained in the gas. At point E over here, the gas rate is high enough to cause excessive entrainment. So, you will have excessive entrainment over here. Now, the tray efficiency falls to a unacceptable level at point F. The tray gets flooded and is inoperable. So, you can see entrainment flooding. And the column will be inoperable. The tray does not operate satisfactorily if the gas rate is kept on decreasing. Now, if we also decrease the gas rate, what happens? Let us see. At a gas rate corresponding to point W, over here. The gas pressure drop across the tray decreases to the extent that the some liquid start leaking through the tray holes. If that is happens, then we have a weeping. This weeping of the tray, as discussed before, will happen as the gas rate is further reduced to point L over here. So, what happens? The weeping rate increases significantly, causing deterioration of the performance of the tray, and the tray should be operated above this point, otherwise damping will happen or heavy weeping will happen. If the gas throughput is yet reduced to point D, damping of liquid starts. Okay. So, in this region, so damping will start. Under such a condition, most of the liquid passes through the tray holes and little if any flows into the downcomer. So, all the liquids which will come from the top tray will pass through the perforation and it will fall down directly without any flows or little flows through the downcomer. The operable limits of a tray in respect of gas and liquid flow rates depends on the tray design, temperature, pressure conditions as well as properties of the liquid and the vapor phases. So, this will decide about the operation limit of the gas and the liquid. Now, another important thing is the turn down ratio. A column designed for a particular capacity may have to be operated at an enhanced or reduced capacity depending upon the changes in the production rate in the plant. So, due to various factors. So, we need to have an operational flexibility for our design. It is therefore desirable that the trays have some degree of flexibility to operate over a range of throughput around the design capacity. Such flexibility is expressed in terms of turn down ratio, which is defined as the ratio of the design vapor throughput to the minimum operable throughput. So, turn down ratio for shift trays have a very low turn down ratio of about 2 for shift trays. For valve trays normally have a turn down ratio of 4 and bubble cap tray have a still larger turn down ratio. Now, the tray spacing. Tray spacing is the distance or gap between the consecutive tray in a column. An accurate tray spacing is important for quite a few reasons. The rate of entrainment strongly depends upon the tray spacing, and as we know, the entrainment actually reduces the performance of the tray. Not only that, tray spacing also important in case of the froth formation and the flooding of the column, which greatly reduce to the tray efficiency. If a larger spacing is provided, most of the liquid droplets descends back to the tray, reducing the entrainment. If a larger spacing is provided, most of the liquid droplets descend back to the tray, reducing the entrainment. The column can operate at a greater superficial gas velocity and a smaller column diameter can be used for a given throughput. But the column height increases if the same number of tray have been accommodated. Hence, a trade off between a smaller column diameter and a larger height has to be struck. So, we have to optimize the column diameter as well as the number of trays. The tray spacing varies from a pretty wide range from 8 to 36 inches. For a column of 4 feet or larger in diameter, a tray spacing of 18 to 24 inches is adequate. So, these are the typical values which is used. With this, thank you for your attention and attending to this lecture. In the next lecture, we will discuss more about the design of the tray column, and we will try to solve some problems on this.